So we're looking at Gibbs free energy right now. So Gibbs free energy is basically equal to internal energy subtract absolute temperature times final entropy plus PV, which is basically absolute pressure times final volume. Another easier way to see this is basically this one here. Change in Gibbs free energy is equal to change in internal energy subtract absolute temperature times change in, well, entropy. One thing you have to keep in mind is that this one here, TS, is basically energy one can get from the system's environment by heating. So examples are maybe combustion, light, electromagnetics, explosions, anything that can generate some kind of energy. And it helps if it's heat. That is actually one of the reasons why it says change of 8, enthalpy change, which is basically measured in kilojoules. This one here will likely be measured in, well, this one here will likely be measured in kilojoules, but you have to keep in mind absolute temperature will be in kelvins and final entropy will not be in kelvins. So once you subtract the difference between internal energy and, well, this one here, you can just add the work to give the system final volume at a constant pressure. So the pressure will be constant, but then you just basically look at if the volume in the system has changed, like did it go from a low volume to a high volume, you minus those two and you add it together with the internal energy subtract, this one here. And once you have that, you just add the final volume and you can get the Gibbs free energy. So Gibbs free energy is measured in kilojoules mole to the power of -1. Enthalpy change is measured in kilojoules mole to the power of -1. That makes sense because this is the units you're going to be using for Gibbs free energy. And then basically temperature is kelvins and entropy is in joules, K exponent -1 times moles negative. This is not really important. Just keep in mind it's measured in kilojoules mole inverse of 1. Okay, so here's a very interesting graph of how Gibbs free energy works. As you can see, if there's a positive work done in the system, what will end up happening is the system, here's a positive, it'll work. As this thing goes positive, as the PV becomes more positive, this negative TS is going to become more negative. So here it's U, internal energy, which is basically energy needed to create a system. Here's F, which is basically U, this one here, internal energy subtract T of S. So energy needed to create a system minus the energy you can get from the environment. So once you've added this to the internal energy, you'll get an F, so the Helmholtz free energy. Now enthalpy is basically energy in the internal environment plus the work given to the system, internal energy plus PV, so U plus W. So H is basically energy needed to create a system plus the work needed to make room for it. That makes sense. Now Gibbs free energy total is basically you take all this and you add them together. You put the positive internal energy, you add it to the PV work, the enthalpy. So basically you add the enthalpy plus the T of S, enthalpy, plus the negative T of S, okay, if you can see it now, much easier, enthalpy, which is basically internal energy plus PV, subtract T of theta S, and you can get the Gibbs free energy. I hope that's an easier way to conceptualize this problem instead of looking at it in separate groups. So here's a much more conceptual method. So delta G, which is Gibbs free energy, is change in free energy. Energy is available to do work and predicts if reaction is favorable. That makes sense. Now, enthalpy is change in enthalpy, which is basically heat released or absorbed and does not predict if a reaction is favorable. So this is U plus PV. Subtract T, which is times theta times the change of entropy. So change in enthalpy, heat released or absorbed, and does not predict if the reaction is favorable, and T is basically absolute temperature. Here's a graph of, say, enthalpy. So we have the Gibbs free energy. If it's There's going to be a negative Gibbs free energy if it's an exergonic reaction, and then after that, what we have here is an activation energy, and then this is basically the change. Like, this is the initial and final. So as you can see here, as the reaction goes on, it goes from a higher energy to a lower energy, which is a Gibbs free energy, what we'd call an exergonic reaction. Now this change in G, Gibbs free energy, is the activation energy, which is the energy you need for the reaction to fully occur. So a catalyst is usually located in the section.